Okay, before I get into section 1.2 material, I want to finish up one thing that we haven't really talked about in section 1.1. And that is when to simplify the problem, simplify, if you're given a limit, to simplify it first before you come to your conclusion, the situation. So what I'm going to do, I'm going to open up on my iPad here. I'm going to show you an example of what I'm talking about where you can simplify it first and as a result get a solution that doesn't have a problem. You know, it does, like this problem that I've put on my iPad here. Limit as x goes to -3 of x squared minus 9 over x plus 3. Notice that that causes the denominator to be equal to 0. X equal to negative, as x gets closer to -3, the denominator is going to 0. Okay, but mathematically, if you can simplify this first, you will get the result that you're needing to answer the question. What is the limit? So remember, the idea is to factor it. And one of the situations that you can do is factor the numerator in this case. You can recognize it's the difference of two squares. So you can see that it's going to be x plus 3 and x minus 3. And therefore, that'll simplify. The x plus 3 will cancel out. So this is equal to the limit as x goes to -3 of x plus 3 times x minus 3 over x plus 3. And those cancel. And as a result, the answer to the problem is going to be the same as the limit as x goes to -3 of x minus 3. That answer, that now has no problems. I can just plug in the -3 and get the answer. I get -3 minus 3, which is -6. And so the answer to the original question of this question right here, the answer is that is equal to -6. And I want to point this out on Desmos. Let me show you here. Okay, notice that that is a line. That is a line. And then when you went back to the iPad, the answer was, it was the same as the limit as x goes to -3 of x minus 3, which has a y-intercept of -3 and the slope of +1. It's the same as the slope, the equation x minus 3, and that's the equation of that line when you cancel out those x plus 3's. But there's a glitch here. There's a catch to this. And the situation is that, notice the denominator cannot be equal to 0. So in this problem in Desmos, on your TI calculators, if you zoom in close small enough, you can see actual pixels missing where there's a hole. You know, we're at x equals -3. On Desmos, you kind of, if you click on the file and get closer and closer, I'm at x equals -2 there. -2 getting closer and closer to 3. Notice at -3, it's undefined. And you see, there's the way they've got the diagram, you can see that there is a hole in the graph underneath my cursor there. If you go to the left, it's solid. If you go to the right, it's solid. But if you're at -3, you've got a hole there. That's indicating that there is a hole. And you get on your TI calculator, that's going to be the same thing. You'll have that, the hole, it's undefined at that point. Okay, with that, I want to get back to something in the text. Let me go back to the text here and point out that one of the things I wanted to show you in the table of contents, let's go to section 1.2, is the fact that 1.2, look at all of these situations that are there. It's saying find the limit of a sum, a difference, of a product. In this situation, there's a general standing rule. It's like in several different things with different derivatives and antiderivatives. There's rules that hold, and the limit of a sum is equal to the sum of the limits. The limit of a difference is equal to the difference of the limits. All of these are true. The limit of a product is equal to the product of the limits. So for example, the situation right here, 0.2, the limit of a sum, here we go. So if you've got the limit of a sum of two functions, well, that's equal to the sum of the two limits, okay? And it's the same with the difference, this, you know, and all of these rules hold, and the total summary I want to show you, if you go to the table of contents under limits and continuity, I want to look at section 1.2. And if you go to the summary at the end, it lists all of the circumstances that we're contending with there. So the limit of a product is product limits. They're all there at the end of the situation. But one other thing I want to point to, I'm going to go back to my iPad real quickly here. Well, it's these two up here. The limit of a constant as x goes to c, the limit of a constant is the constant. And the limit as x goes to c of x is c. Let's take a look at that. I'm going to show you that on my iPad real quickly here. Let's go back to stop share, and let's go back to my iPad. The two things I'm pointing to there are, the one rule was that the limit the limit as x goes to c of a constant, is equal to a. And that's like saying this. If we've got a function y equals 2, all right, then the limit as x goes to 3 of 2, that's the function, y equals 2. What does that graph look like? Y equals 2 looks like this. It's the line, this is the line that goes right there. That's the line y equals 2. What's the limit as x goes to 3 of 2? What's as x goes to 3? What's the answer? It's 2. So no matter what x is going to, the answer is 2 if it's a constant. And the second one was this, that the limit as x goes to c of x, okay? That's saying the line y equals x. What does that look like? All right? Well, that looks like y equals x, looks like this, right? All right? Well, as x goes to c, what's x going to be? C. That's the situation. So in other words, if you've got the limit as x goes to 2 of x, as x goes to 2, then y is equal to, plug it into 2. That's equal to 2. Is the limit as x goes to 7 of x is equal to 7. Okay, et cetera, et cetera. Wanted to make sure you saw those and where the summaries were, and I wanted you to see that. Make sure you cancel in section 2.1 before you determine the final limit situation. Okay, that's it. And keep going. There'll be another lesson coming soon.